Okay, so let us start with today's session. Okay. So can anyone just speak or like just type what all we looked into last class? Like if anyone is there from last class, just if anyone want to like volunteer to summarize. Okay. So yeah, so last class we started with CRE, like we looked into the basics of CRE. We looked into rate of reaction, and the types of ideal reactors. So we started with how to write the rate equation, and from then we went on to see how we can derive rate equations for different orders of reaction and different types of reactions. And then we looked into the temperature dependency of rate equation. So we looked into the Arrhenius theory, and the other two theories are collision theory and transition state theory. And yeah, then we got on with deriving the general equations for rate of reactions for zero order, first order, second order, and so on. Then we started with the ideal reactors, and yesterday we looked into the batch reactor. We saw that by writing the material balance of the batch reactor. So whatever reactant is going in minus the reactant that is coming out will be equal to the reactant that got reacted plus the reactant that got accumulated. The mass balance that is shown here. So using this, we can derive the general equation for batch reactors, the general equation comes out like this. And we looked at how we can graphically represent batch reactors with respect to different kinds of graphs and so on. So today we'll be looking into the continuous reactors. And the continuous reactors are PFR or plug flow reactor, or CSTR, which is continuous stirred tank reactor. So the basic concepts for with respect to the design equations for these continuous reactors are also same or similar as what we saw in the batch reactor. So what we do here is also just take the material balance, and from the material balance we can derive the general design equations for these continuous reactors. So so when we come to continuous reactors, there is a term that we need to learn. So which is called space-time. So space-time, generally represented as tau, is is the time required to process one reactor volume. So let's say we have a reactor. Let's say we have a CSTR of volume V, or a plug flow, or a batch, or any continuous reactor. So let's say the volume is V. What is the, let's say this V is somewhere around, let's say 10 meter cube. So what is the time required for the reactor to process 10 meter cube of feed? The time required for processing one reactor volume. So this reactor volume is 10 meter cube. So how much time it is required by this reactor to process 10 meter cube of feed basically. So this is what is known as tau, space time. And this tau is equal to volume of the reactor by volumetric flow rate into the reactor. That is V by mu 0. And the unit of tau is basically, for volume we have meter cube, and the flow rate, volumetric flow rate, it is meter cube per second. So the unit comes out to be second. Okay. So again, space time is the time required for the reactor to process one reactor volume of a reactant. So this is called as space time. And then the next term is space velocity. And this is generally represented as S. So the space velocity is basically number of reactor volumes processed in a unit time. So space velocity means, so the same case, let's take uh, the reactor and the volume V is 10. So let's say this volume of feed is 50. So space velocity basically means the number of reactor volumes processed in a unit time. So here this volume of feed is basically 5 times the volume of the reactor. So let's say per second this reactor is being fed 50 meter cube. That means 5 times the reactor volume is being processed by this reactor in a unit time. So that is represented as space velocity. So again, space velocity is the number of reactor volumes processed in a unit time. So here, if we take, if we assume that 50 meter cube of feed is being fed into a reactor which is having a volume of 10 meter cube per unit time, that means 5 times the volume of the reactor is being processed by the reactor in a unit time. So this is the significance of space velocity. And the space velocity can be written as S is equal to 1 by tau, or basically the inverse of tau, that is mu 0 by V. And the unit here is second inverse. So this is space velocity. So these two terms come a lot when we try to solve problems with regards to continuous reactors like the PFR or CSTR. So it is important to know their significance and how to calculate them. And when we talk about the design equations of these continuous reactors, tau is what we talk about. So we design the reactor based on the value of tau. All right. Um, let's move on. So the first one is the continuous stirred tank reactor or CSTR. So some of the assumptions that we take for ideal CSTR. The first assumption is perfect mixing. That means the the system inside is homogeneous. The second one, total volume of the reactor is available for reaction. The third one is the composition inside the CSTR is equal to composition in the outlet. So let's see what this means. So we represent the CSTR like this. So this is a stirrer of the CSTR. This is Ca0, which is the inlet concentration of the reactant, and this is Ca, the outlet reactant of the outlet composition of the reactant. So the first one assumption is that whatever is inside this CSTR is homogeneous. That is, the mixing is 100% perfect. The second assumption is that total volume of the reactor is available. So let's say if V is the volume of the reactor, the whole of V is available for the reaction to take place. So these are the assumptions again for ideal CSTR. Note the term ideal CSTR. And then the third assumption is that the composition inside the CSTR is equal to the composition in the outlet. So the outlet composition is given as Ca. So at any point inside the CSTR, the composition is again Ca. So this is the third assumption. Okay. So when we come to the design equation, if we can start by writing the material balance in minus out is equal to, or A in minus A out is equal to A reacted plus A accumulated. Okay. So let's say Fa0 is the initial molar flow. So this is mole per second or mole per hour and so on. For molar flow, the initial molar flow, let us represent it as Fa0, and Fa is the final molar flow of A. So A in minus A out is equal to A reacted plus A accumulated. The assumption for continuous reactors is that there is no accumulation inside the reactor. So this A accumulated will be 0. Okay. A in. So when we talk about the A in terms of molar flow rate, it is Fa0, and A out is equal to minus Fa. This is equal to A reacted, which is basically minus Ra. Okay. Fine. Now we saw that Ca is equal to Ca0 into 1 minus Xa. And similarly, Fa is also is equal to Fa0 into 1 minus Xa. So just substitute this Fa here, and if we expand on this, we'll get the final equation. So we'll just go write it. Fa0 minus Fa0 plus Fa0 Xa is equal to minus Ra. Ra into V, sorry. Yeah. Okay. So Fa0 and Fa0 gets cancelled. So we'll get the final equation Fa0 Xa is equal to minus Ra into V. So V by Fa0 is equal to V by Fa0 Xa by minus Ra. So this is one form of the design equation for CSTR. We can make new forms of this same equation by just having some manipulations to this term. So let's say we are multiplying CA0 in both the sides. V CA0 by FA0 is equal to CA0 into XA by minus RA. Okay, so let's take the left hand side. V CA0 and FA0. So V is what? Meter cube. CA0 is mole per meter cube, the whole by FA0, which is basically mole per second. And this comes out to be second, and that is the unit of tau. Okay, so tau is equal to CA0 XA by minus RA. So this is another form of the general equation for CSTR in terms of space-time tau. And we can again make this into a different form. So we know that CA is equal to CA0 into 1 minus XA. So basically CA0 minus CA is equal to CA0 XA. So just substitute this CA0 XA here and we'll get tau is equal to CA0 minus CA by minus R. So these three are the usual notations for the design equation for a CSTR. In some cases, you can even use this notation as well. So yeah, so that is the design equation for CSTR. Now, if you want to uh, say uh, represent this graphically, 1 by minus RA, and this is XA. It will come something like this. Okay, so we'll get the operating curve like this. Now the area under this, the area covered by this curve. So previously when we looked at batch reactor, it was the area under the curve. But when it comes to CSTR, it is the area covered by the curve. So this whole area is equal to tau by CA0. Okay. And also another point is this point, let's say this point P is known as the operating point of CSTR. Okay. Now in a similar fashion, we can work out the material balances for PFR as well, and we can find the design equation for PFR. Now, before moving to CSTR, I hope this is clear to everyone. So basically what we did, we just took the material balance and we just simplified it and we got a design equation for CSTR. And this is what we'll be repeating again for PFR. And let's see how we do for PFR. Okay. So for PFR, the assumptions for ideal PFR. The first one is velocity is constant for all molecules. So that means all molecules moving inside a PFR is moving with the same velocity. So whatever, okay, let's look into that bit. Now, there is no axial mixing. Axial mixing is equal to 0, but radial mixing is there. So we'll see how this is affecting it. And the third is residence time for all molecules are same. Okay, so a PFR is basically a tubular reactor. Okay, so usually a PFR is represented like this, like a tube. The first and third assumptions are meaning implying almost the same thing. So let's say a molecule enters this PFR at time t equal to 0. Let's say these four molecules are entering the PFR at time t is equal to 0. Then at time t equal to, let's say, let's take some arbitrary value t dash. At t dash, all these four molecules will be exiting the PFR. Okay, that means all these molecules are traveling at the same velocity throughout the CSTR. I mean, so throughout the PFR, and the residence time. The time residence time is basically the time during which the molecule or the reactant molecule stays inside the reactor. This time is same for all these four molecules. So that is the first and third assumption. The second assumption, which means, so let's say, I know, let's take two sets of these molecules. So first this set of molecule first entered, and then this set of molecule entered. What it means is axial mixing is 0. So mixing between these two layers does not happen. Okay, that means this is axial and this is radial. So the axial mixing does not occur here. Instead, a radial mixing of molecules of the same layer can happen. So that is infinity. So that is the second assumption here. Axial mixing is 0 and radial mixing is infinity. Now, the material balance for this, I'll give this as a homework for you. So you guys try it out and see. So you can refer, textbooks as well. There are a lot of good textbooks available for CRE. So you refer this, and by doing the material balance, we can see that tau is equal to integral of 0 to xa Ca0 into dxa by minus Ra. Or we can even write this as tau from Ca0 to Ca minus dca by minus Ra. Right. And this tau you can even write it as Vca0 by Fa0. So these are the general forms of design equation for a PFR. Right. So if this is clear, let's move on to just one more concept before we try to solve some problems. So any doubts so far? Okay. Fine. If there are no doubts, let's move on to one more concept. Recycle reactors. So a recycle reactor is basically, you know what a recycle means, right? It is just taking a portion of the product and just recirculating it back into the reaction system. So let's take this is our PFR and this is our product on the right side. We take a part of this and recycle it back into the PFR reactor. Okay, so this is a recycled reactor. Now, the recycle ratio, let's say, where is it? So let's say nu zero is the initial volumetric flow rate of the reactant, with Ca0 as its initial concentration, Fa0 as its initial molar flow rate. Then here it will be nu 1 and Ca1 and Fa1 at this point. Okay, and then at this point it will be nu 2 and Ca2 and Fa2. Then finally it will be nu F C Ca2, which will be equal to CaF, because there is no reaction that is happening after this point, so the concentration will remain the same. Okay, now let's say mu F is the volumetric flow rate of the recycle. Then the recycle ratio is equal to where is mu 3? Just a second, guys. Okay. Okay. Yeah, sorry about that. Okay. Okay. Um, yeah. Okay. Oh, there is a mistake here. Fine. So okay. So let's get back to this. So yeah, just summarizing again, we have a PFR with the recycle, and the initial flow rate is nu zero, and the final flow rate is nu F. Let's say nu 3 is the flow rate of the recycle. Then recycle ratio is equal to R, which is basically nu 3 by nu F. Okay, so this is called as the recycle ratio, or basically the flow rate of recycle part here divided by the final flow rate. So that is called as the recycled ratio for a recycle reactor. And for this also, we can find the general design equation by using the normal material balance, and the design equation comes to be tau, which is VCA0 by FA0 is equal to R plus 1 into CAF to CA0 plus RCAF by R plus 1. So this is nothing but CA1. the concentration here. Okay, so this into integral from CA1 to CAF minus DCA by minus RA. So this is the general equation for a recycled PFR, recycled reactor or a recycled plug flow reactor. Okay, so this is just a brief concept that I wanted to like just touch before we move into the problems. So yeah, the other form, we can have the other form as well. V by Fa0 is equal to R plus 1 into XAF by R by R plus 1 XAF dXA by minus RA. So this is also a form of the design equation that we can derive for recycled PFR reactor by using material balances. Okay. So just take a note of this formula, and again, I would suggest you guys try to like work out the material balance and see how we can derive this formula for a recycled reactor. So for like more than 1.5 class, we have been looking into a few of these concepts related to CRE, the basics of reactions and reactors. It's high time we move into solving some of the questions from previous year gates questions. So any doubts regarding this? Okay, one more thing I think we should learn before we move on. So variable volume system. So the thing about questions from CRE for GATE is that it touches a lot of multiple concepts. So you need to know and remember multiple concepts when you like try to solve these GATE level questions. So far we did a lot of derivations. We derived a lot of equations for reactors and reactions, and all these things are based on constant volume systems, or basically if the reaction is liquid phase, we assume that it is a constant volume system. The reason being, it can be approximated that even if temperature varies or temperature increases, the density or the volume of liquid does not change that much. Okay, so such systems you can say, constant volume systems. And usually liquid phase reactions are assumed to be constant volume systems. But when it comes to gas phase, these are variable volume systems. And the reason is gases tend to change in density and volume with respect to temperature or pressure. Like we have learned a lot of you might have learned in thermodynamics the ideal gas relations, PV is equal to nRT, or the van der Waals equation of state. So the change in volume for gases is much more apparent when the change in pressure or temperature happens. And so for these kinds of systems, the variable volume systems, we need to accommodate for a term which signifies the change in volume of the system, and that term is basically represented as epsilon. So this epsilon is nothing but change in moles in the system divided by total moles initially fed to the system or fed to the reactor. Okay. So let's say take a brief example. A gives B plus C. So this means basically 1 mole of A gives 1 mole of B and 1 mole of C. So the epsilon here is change in moles. So say when we say change in moles, it is basically the difference between the total moles of product, which is 1 plus 1, minus total moles of reactant here, and that is 1. So this is 1 plus 1 minus 1 by total moles initially fed to the reactor, and that is just pure A, and that is 1 mole, so that is 1. So this is basically 2 minus 1 by 1, and that is 1. Okay. Now, if we take a different reaction, like let's say A gives B plus C plus D, then 1 mole of A gives 1 mole of B and 1 mole of C and 1 mole of D, and epsilon will be 3, which is the total moles of product, minus 1 by 1, and that is 2, right? This is significant in one more case. Let's say instead of having pure A as my feed, I'm having inerts as well. So there are some reactions, like you might have learned the equilibrium in thermodynamics. So adding inerts in some reactions actually help in better conversion for the reaction. And so, adding inerts is something that is common in a lot of cases. So and let's say the same reaction, A plus inerts gives B plus C. Now, when we try to do the epsilon for here, it is important to know that this inert does not react. So that means when we look at the product, the inerts come here as well. Okay. So when we try to do the epsilon here, 1 mole of A, and let's say we take 1 mole of inerts, give us 1 mole of B and 1 mole of C, and this inert doesn't react, so 1 mole of inerts here as well. Now, if we write the epsilon, it is the sum of moles of products, which is 1 plus 1 plus 1 minus total moles of the feed, that is 1 plus 1. And this one represents B, this one represents C, this one represents inerts. And similarly, A and inerts by 1 plus 1. That is A and I. So basically, this is 3 minus 2 by 2, and that is 0.5. Okay, so this is how you can try to take into account the change in volume, especially when we are dealing with gas phase reactions, right? So yeah, this is also an important concept that we should remember while we solve these problems. So any doubts so far? We'll quickly look into two problems. If there are no doubts, I think we should move on to the problems. Okay, fine. Let's move towards solving some problems. Hello, everyone. Okay, is this, how do I go full screen? Okay. Okay, so just read this question. So basically this question, so we have a reaction, an autocatalytic reaction. So autocatalytic reactions, they have given the reaction A plus B giving 2B. So that means the reactant itself is one of the, the product itself is one of the reactants. So A will react with B and it will give 2 moles of B as the product. So such a reaction is called autocatalytic reaction. So in this question, the following autocatalytic reaction is happening as A plus B gives 2B and the rate of reaction is given as zero point 0.1 CaCb. That means this is a second order reaction. And this reaction is carried out in an ideal CSTR operating at steady state. Pure A at 1 mole per liter is fed and 90% of A is converted in the CSTR. And we need to find the space time of this CSTR in seconds. So basically what we have to do here is just apply the design equation of the CSTR. So we learned how to derive the design equation of CSTR, and we have been given some data for it, and we just have to directly apply this equation, and we need to find out the space time of the CSTR in seconds. So let us do a brief pictorial representation of the given question here. We have a CSTR and let's say tau is its space time which we need to find. They have given Ca0 is equal to 1 and there is no Cb0 because the feed is pure A. The final final concentrations are Ca and Cb. The reaction is an autocatalytic one, which is A plus B giving 2B with the reaction rate is equal to zero point 0.1 CaCb, and this is a second order reaction. So the design equation for CSTR is tau is equal to Ca0 minus Ca by minus Ra. This is what we just learned in the previous slides. So we have Ca0 here. They have given the conversion which is 90%. So we can find Ca as well. And Ca is equal to Ca0 into 1 minus Xa. And the minus Ra is given in terms of 0.1 CaCb. So given conversion is 0.9. So Ca is basically Ca0 into 1 minus Xa, and that will be 1 minus 0.9 into 1, and that is 0.1. So we have Ca0. So we have Ca0, we have Ca, and now let us expand on Ra. So Ra is 0.1 CaCb. Now the unknown here is Cb. Everything else we have to find the space-time tau. So how can we find Cb here? Okay. For autocatalytic reactions, the total concentration is constant. So we can write this using this equation. So what we mean to say is at any point in an autocatalytic reaction, the total concentration in the reactor is always constant. So that means the sum of the reactants initially fed will be equal to sum of composition of reactant that is coming out of the reactor, and let us say it is equal to C which is an arbitrary value, and this holds true for an autocatalytic reaction at any time. Okay, so basically Ca0 plus Cb0 is equal to Ca plus Cb for an autocatalytic reaction. So they have given us the value of Ca0 and Cb0. So the value for Ca0 is 1, Cb0 is 0, and Ca we just found out as 0.1. So from this we can find the value of Cb, which comes to be 0.9 mole per liter. So now we have all the values required to find the space-time. Just substitute these values in the equation. So we just found out Cb from this balance. Ca0 plus Cb0 is equal to Ca plus Cb. So this holds true only for autocatalytic reactions, and this is true for an autocatalytic reaction at any time. So using this, we found the concentration of Cb. We had the compositions or concentrations of Ca0, Ca from the question. Now we have all the values required to find the space-time. We just have to substitute it and find the space-time. So the final space-time will come out to be 100 seconds. So again, to recap what we did here, we just started with the basic design equation for a CSTR. We have the basic equation as tau is equal to Ca0 minus Ca by minus Ra. They have given us the value of Ca0 as 1, and Ca we can find because they have given that conversion of A is 90%. So 90% of A got converted into the product B. So that means uh, the Ca will be equal to Ca0 into 1 minus Xa. So whatever is remaining after the conversion of A is basically Ca. So that Ca will be 0.1. Then to find Cb, we can use this balance for autocatalytic reactions, which means the composition at all times in an autocatalytic reaction will be constant. So using this, we can find the value of Cb as well, and we just have to substitute all these values in the design equation for CSTR, and the final space time will come out to be 100 seconds. Is this clear? Okay. So this is like as you can see, there are a lot of basic concepts that you need to be good with, or like you need to know when you want to solve such questions. So we needed concepts from the reaction rate equation, or the autocatalytic reactions, or the basic design equation for CSTR. So all these small concepts constitute a question from GATE or any kind of numerical problem from CRE. So if this is clear, let us move on to the next question. Just read through this question. Okay, fine. So this question, so this is a special reaction network. You can say this is a cyclic reaction network. So A gives reversibly gives B, reversibly gives C. So far in the slides we looked at one directional reactions. So like it is either A gives B or A gives B plus C and so on. So here it is a reversible reaction. So A will give B, and B can again get back to the original A as well through a reversible reaction or a backward reaction. So, such reactions are called reversible reactions, and the system here is a cyclic reversible reaction. So, A reversibly gives B, which reversibly gives C, and this C reversibly gives A as well. Okay, so we have such a reaction network, and the rate constants, most of the rate constants of this reaction network is given here. So, again, this is a liquid phase reaction. So it is mentioned that the following homogeneous liquid phase reactions are at equilibrium. The values of rate constants are given. So K1, which is the rate constant of the forward reaction from A to B, is 0.1, and K minus 1, which is the reaction rate constant of the backward reaction from B to A, is 0.2. Then K2, which is the rate constant, forward reaction rate constant for B to C, as 1. K minus 2 is the backward reaction from C to B, which is given as 10. And K3, which is the forward reaction from C to A, given as 10. So we need to find the only leftover rate constant, which is K minus 3, or the reaction rate constant for the backward reaction from A to C. Okay. So let us see how we can solve these systems. So the concept that you need to remember here are about reversible reactions and equilibrium constants. So let us write the equilibrium constants. Yeah. So the given system is cyclic reversible system, and these are also at equilibrium. Okay, equilibrium means rate of reaction is 0. For reversible reactions, we can define equilibrium constants. So we can define the equilibrium constants here as K, capital K, is equal to forward reaction rate constant by backward reaction rate constant. Okay. Yeah. So capital K is basically the ratio of forward reaction rate constant to backward reaction rate constant. So here, for example, if we take the system of A reversibly gives B, this equilibrium constant capital K1 will be small k1, which is the forward reaction rate constant from A to B, by K minus 1, which is the backward reaction rate constant from B to A. So in such a fashion, we can define the equilibrium constants for all these three reversible reactions. So K1 we can define as K1 by K minus 1, K2 is K2 by K minus 2, and K3 will be K3 by K minus 3. So we have been given a lot of these values for K1, K minus 1, K2, K minus 2, and K3. So we can substitute these values here, and we can find the corresponding equilibrium constants values. Sorry. Right. So let us just substitute these values here. So we have K1 as zero point 0.1 and K minus 1 as zero point 0.2, and the ratio will be zero point 0.5. Similarly, the equilibrium constant for K2 will be 1 by 10, and that is zero point 0.1. Now when it comes to K3, the equilibrium constant K3, we have the forward rate constant small k3, but we need to find K minus 3. So let's see how we can proceed from this. Right. So, is this clear with regards to the equilibrium constants and how we calculated these equilibrium constants using the reaction rate constants? Okay, fine. So, for cyclic reversible system in equilibrium, the product of all the equilibrium constants will be equal to 1. So this is something we need to remember when it comes to cyclic reversible systems at equilibrium. So that means product of K1, K2 and K3, the equilibrium constants will be equal to 1. Okay. So here again repeating, the product of equilibrium constants for all the reactions included in the cyclic reversible system which is at equilibrium will be 1. So we'll be using this formula K1 into K2 into K3 is equal to 1 to find the value of K3, the capital K3, and from the equilibrium constant K3 we can find the value of K minus 3. So that is what we'll be doing here. So we have K1 and K2 values which we just found out. We just apply this or substitute this in the equation K1 into K2 into K3 is equal to 1, and we will get the value of K3 as 1 by zero point 0.1 into zero point 0.5, and K3 will be 1 by 0.05, and that will be 20. Now equilibrium constant K3 is equal to forward reaction constant K3 by backward reaction rate constant K minus 3. And they have given the value of K3, the forward reaction rate constant, and we just found out the value for the equilibrium rate constant K3. So substitute these two values here and we can find the value of K minus 3. So 10 by K minus 3 is equal to 20, and K minus 3 will be 10 by 20, and that will be 0.5. Okay. Uh, Hello. Okay. Yeah. So, yeah, this is the thing that we are following here. So we have the forward reaction rate constants and backward reaction rate constants for three reactions which are cyclic and reversible in nature. Hello. Am I audible?
Yes, sir.
Okay, sorry. Yeah. Some issue with the mic, it seems. Okay. Okay. Fine. So we had, the forward reaction rate constants and backward reaction rate constants for cyclic reversible system with A gives B gives C in a reversible manner. We had to just find one of the rate constants, and for that we use the concept that product of the equilibrium constants of cyclic reversible system at equilibrium will be 1. So we just substituted all the values that we had to find, the equilibrium constants K1 and K2, and we found the unknown, equilibrium constant K3. And from K3, we found out the required value of K minus 3, and that comes out to be zero point 0.5. Okay. So yeah, that is the disconnected. Okay. Sorry, sorry about that. Yeah. Okay. So yeah, um, I guess yeah, we were looking into this question. Okay. So is this clear? Like, do you want me to repeat this question?
No, sir.
Okay. Fine. 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 We'll stop here. So I know, like, there are some more concepts that we should have looked into, but I am leaving it up to you to, like, refer some of these concepts, like, let's say the reversible reactions. So we can derive reaction rates for reversible reactions, like the same way we derived the reaction rates for the, let's say a reaction like A gives B or A gives B plus C. So it's just the same concept. We have to, write it as, DC, using the dCA by dt is equal to K1 CA minus K2 or K minus 1 CB. And like, we just have to do some integration with multiple variables, and we can actually derive, these rate equations for reversible reactions. So if time permits, we'll try to look into it in the next class. And but in any case, I would suggest you guys also, like, try to look into it in the standard textbooks. So we can derive rate equations for reversible reactions. We can derive rate equations for the autocatalytic reaction. So these rate equations are somewhat more elaborate compared to the normal, minus RA is equal to KCA square form. So just try to see or look into these equations and see how, the standard derivations and the standard forms of these, rate equations are. So it will definitely be useful when you are trying to solve these questions. Yeah, so we'll stop here for today. And next class, we'll again continue with questions from basic CRE 1. So most of these questions from CRE 1, are linked to ideal reactors, basically ideal reactors, which includes the concepts of rate of reaction equations. So that is where, we need to remember the different equations for first order and second order and so on. And when it and if reaction like this, a reversible reaction occurs, so it is always better if we can remember or at least know how to derive equations, rate equations for such reactions. So just try to look into these, special reactions like these reversible reactions and autocatalytic reactions, and see how you can derive rate equations for this. And in the next class we'll try to, like, look into some problems. So the problems that I just looked for the next class is actually a bit more lengthy compared to these problems, so you will require a lot of these basic concepts that you need to remember, and you need to apply these concepts to solve these kinds of questions. And these kinds of questions are also very common in almost all the gate exams that you will be attending. So Yeah, do look into these things. So, like for this class, I asked you to look into the how material balance is used to derive the equations for PFR. So that is also one thing. It will be helpful if you can remember how to derive equations for ideal reactors. So just take a look into these, you know, derivations for reaction rates as well as this ideal PFR. And in the next class, we'll resume solving more problems from previous year gates questions. I'll try to stick to the questions that are related to the concepts that we learned so far, and let's see from there on how it goes. All right. So yeah, that's it for today. Thank you for joining, and I'll hope to see you all next Monday.